Hi, in this video we will learn how we can check if two given diagonalizable matrices are invertible or not. Remember that checking similarity of two matrices is not easy. So what we have was that we found some necessary conditions. For example, if A is similar to B, then they have same eigenvalues, they have same determinant, they have same characteristic polynomial. We also know that if A and B are similar, then A is diagonalizable if and only if B is diagonalizable. So two matrices, if one is diagonalizable and one not diagonalizable, they cannot be similar. Okay. Well, the proof of this is easy. You know, A is similar to B. B is diagonalizable means that B is similar to a diagonal matrix. Then this implies that A is similar to a diagonal matrix. That means that A is diagonalizable. By a symmetric argument, you can show that the other way around is also true. But, well, now assume that A and B are two diagonalizable matrices. So let A and B be diagonalizable matrices. Okay, so that necessary condition cannot help us now. These two are diagonalizable. Is there any way that I can determine if these two guys are symmetric or not? And this is the theorem, or, well, let me write proposition, says that A and B, when they are diagonalizable, A is similar to B if and only if they have same eigen values with the same multiplicity. So if you list all the eigenvalues, lambda 1, lambda 2 up to lambda n, then they will be the same thing. Okay. Well, this is equivalent to saying that they have the same characteristic polynomial. So when it comes to the characteristic polynomial, when it comes to the diagonalizable matrices, you just check if these two matrices are they have the same characteristic polynomial or not. If they have, then they are similar. Well, checking this is not difficult. See, if lambda 1 up to lambda n are eigenvalues of A and B, so they have the same eigenvalues, and A and B are diagonalizable, what happens is that, well, we can find an invertible matrix P1 such that P1 inverse A P1 is equal to this diagonal matrix, which is what? Which is lambda 1, lambda 2 up to lambda n. And there is another invertible matrix P2 such that P2 inverse B P2 is equal to the same diagonal matrix. Yes. Then from here, just see two sides. A P1 inverse A P1 is going to be P2 inverse B P2. Then you can multiply both sides by P2 from the left and P2 inverse from the right. Then we will have P2, P1 inverse, A, P1, P2 inverse. This is going to be equal to B. Well, what does similarity mean? Similarity means that we can find an invertible matrix. Let's call it P. Well, I call this guy P. So P is P1, P2 inverse. Inverse of this guy is going to be, remember when you find the inverse of product, you do find the inverse of each one and then multiply in the other order. So first the inverse of P2 inverse times P1 inverse. And this is the same thing as P2 times P1 inverse. And as you can see, this is the P inverse A. And this means what? This means that A is similar to B. When it comes to diagonalizable matrices, checking similarity is easy. Similarity is equivalent to having same eigenvalues. But more you can do, you can find even the matrix, the invertible matrix P, such that P1, P inverse AP is equal to matrix B. Okay, let's do an example for this. Paste. Yeah. So two matrices here we have, and as you can see, these guys are, yeah. A is, this is my solution. A is diagonalizable. Why is it? Well, because it's easy, because A has two distinct eigenvalues. A has two distinct eigenvalues. Lambda equal to 1, lambda 1, and lambda 2 is equal to 2. And B is diagonalizable because of the same argument. It has two distinct eigenvalues, again 1 and 2. Okay? Now, you can find P1 such that P1 inverse AP is equal to diagonal matrix, which is 1, 2. And we can find P2 such that P2 inverse B is equal times P2 is equal to the diagonal matrix. How we find these ones? Well, these are the eigenvectors. You remember, you find the eigenvectors and put them in the column. So this will be P2. Oh, this is P1 actually. P1 is for A, so I have it here. It is 1, 0 is eigenvector of eigenvalue 1, and negative 1, 1 is another eigenvector of eigenvalue 2. For this guy, for B, the eigenvector for 1 is 1, negative 4, and eigenvector for 2 is 1, negative 3. This is for B. Yeah. And now you see that here I have P2 times P1 inverse A. P1 times P2 inverse is going to be equal to B. So the invertible matrix we are looking for is this guy, P, which is P1. P1 is 1, negative 1, 0, 1. And P2, oops, what, this was P2. Yes, P2 inverse. P2 inverse is negative 3, 1, negative 1, and 4. And this gives us what? Negative 7, negative 2. This is 4, and this is what? 1. So we found the matrix P such that P inverse AP is equal to B. You can check this and make sure that this works nicely. Well, summary, when it comes to diagonalizable matrices, having same eigenvalues is equivalent for these matrices to be similar.